A relaxed study session. I'll be pausing when I need to and explain the things in my own words or summarize after each section and talk through anything that seems interesting. Feel free to chat along, ask questions, or just follow the flow. Let's dig in and learn how these models are actually used and how they are built. So, without much further delay, let's dive in and start learning.
So recently I gave a 30-minute talk on large language models, just kind of like an intro talk. Unfortunately, that talk was not recorded, but a lot of people came to me after the talk and they told me that they really liked the talk. So I thought I would just re-record it and basically put it up on YouTube. So here we go, the busy person's intro to large language models, Director's Cut. Okay, so let's begin. First of all, what is a large language model really? Well, a large language model is just two files, right? There will be two files in this hypothetical directory. So for example, working with the specific example of the Llama 2 70B model, this is a large language model released by Meta AI. And this is basically the Llama series of language models, the second iteration of it. And this is the 70 billion parameter model of this series. So there's multiple models belonging to the Llama 2 series. 7 billion, 13 billion, 34 billion, and 70 billion is the biggest one. Now, many people like this model specifically because it is probably today the most powerful open weights model. So basically the weights and the architecture and a paper was all released by Meta. So anyone can work with this model very easily by themselves. This is unlike many other language models that you might be familiar with. For example, if you're using ChatGPT or something like that, the model architecture was never released. It is owned by OpenAI, and you're allowed to use the language model through a web interface, but you don't have actually access to that model. So in this case, the Llama 2 70B model is really just two files on your file system, the parameters file and the run, some kind of a code that runs those parameters. So the parameters are basically the weights or the parameters of this neural network that is the language model. We'll go into that in a bit. Because this is a 70 billion parameter model, every one of those parameters is stored as 2 bytes. And so therefore, the parameters file here is 140 gigabytes. And it's 2 bytes because this is a float 16 number as the data type. Now, in addition to these parameters, that's just like a large list of parameters for that neural network. You also need something that runs that neural network. And this piece of code is implemented in our run file. Now, this could be a C file or a Python file or any other programming language, really. It can be written in any arbitrary language, but C is sort of like a very simple language, just to give you a sense. And it would only require about 500 lines of C with no other dependencies to implement the neural network architecture and that uses basically the parameters to run the model. So it's only these two files. You can take these two files and you can take your MacBook. And this is a fully self-contained package. This is everything that's necessary. You don't need any connectivity to the internet or anything else. You can take these two files, you compile your C code, you get a binary that you can point at the parameters, and you can talk to this language model. So for example, you can send it text, like for example, write a poem about the company Scale AI, and this language model will start generating text. And in this case, it will follow the directions and give you a poem about Scale AI. Now, the reason that I'm picking on Scale AI here, and you're going to see that throughout the talk, is because the event that I originally presented this talk with was run by Scale AI. And so I'm picking on them throughout the slides a little bit, just in an effort to make it concrete. So this is how we can run the model. It just requires two files, just requires a MacBook. I'm slightly cheating here because this was not actually, in terms of the speed of this video here, this was not running a 70 billion parameter model. It was only running a 7 billion parameter model. A 70B would be running about 10 times slower, but I wanted to give you an idea of sort of just the text generation and what that looks like. So not a lot is necessary to run the model. This is a very small package, but the computational complexity really comes in when we'd like to get those parameters. So how do we get the parameters and where are they from? Because whatever's in the run.c file, the neural network architecture and sort of the forward pass of that network, everything is algorithmically understood and open and so on. But the magic really is in the parameters and how do we obtain them. So to obtain the parameters,
Okay, that's the end of section 1 there. So let me summarize it quickly. So as Andre explained, so whenever you talk about an LLM, or like we use LLM in our day-to-day life now, we use ChatGPT, we use Gemini, and a lot of other ones. So ChatGPT, Gemini, all these are proprietary models by OpenAI and Google. But there are other LLM models which are open source and which can be used, open source pre-trained, which can be used by anybody. And then we can just run those LLMs in our computer and then run the inference on it. What do I mean when what is inference? Basically, as he explained there. So this OpenAI and Gemini, these are like proprietary, and we do not have the source code for that. But when you look into that one, basically LLMs are based or two main files. One is the parameters or the weights, and the other one is the run.c. Run.c was as you mentioned, it's 500 lines of code to run the um, to ask questions and then run it back to the network. We might get more details about it. Let's see. And the parameters files. Parameters file was like 70. Like as you mentioned, Llama was a 70 billion parameter model, and then for that we needed a 140 GB file. So each of the parameter would take 2 bytes approximately as a floating point uh, type. So basically, in order to have these two, there is a like how does this gets value? Like a file which is of 140 GB without any network connectivity or internet is able to answer any questions that we ask around the world. So how is that entire knowledge is compressed within that 70 billion parameters? So that we will know in the next section. So just running this model and then getting the value out of it is called inference. Like run the model locally in your computer, ask any questions, instruct it to write a poem or do perform some instructions, and then it will come back to us with the get back to us with the response or the data. So that is called model inference. But another the 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 thing that we need to understand is how these models are trained, how all that vast knowledge is compressed within that 70 billion parameters. So we will know that in the next section. So how is that 70 billion? How is that vast knowledge is compressed within that 70 billion parameters? We'll know that in the next section. Let's take a small break. I'm getting a call. So after that, let's continue. Okay, let's dive into the next section now and see how those models are trained and what all things that we need to keep in mind when it is done.
Everything is algorithmically understood and open and so on. But the magic really is in the parameters and how do we obtain them. So to obtain the parameters, basically the model training, as we call it, is a lot more involved than model inference, which is the part that I showed you earlier. So model inference is just running it on your MacBook. Model training is a computationally very involved process. So basically what we're doing can best be sort of understood as kind of a compression of a good chunk of internet. So because Llama 2 70B is an open source model, we know quite a bit about how it was trained because Meta released that information in a paper. So these are some of the numbers of what's involved. You basically take a chunk of the internet that is roughly, you should be thinking 10 terabytes of text. This typically comes from like a crawl of the internet. So just imagine just collecting tons of text from all kinds of different websites and collecting it together. So you take a large chunk of internet, then you procure a GPU cluster. These are very specialized computers intended for very heavy computational workloads like training of neural networks. You need about 6,000 GPUs, and you would run this for about 12 days to get a Llama 2 70B. And this would cost you about $2 million. And what this is doing is basically it is compressing this large chunk of text into what you can think of as a kind of a zip file. So these parameters that I showed you in an earlier slide are best kind of thought of as like a zip file of the internet. And in this case, what would come out are these parameters, 140 gigabytes. So you can see that the compression ratio here is roughly like 100x, roughly speaking. But this is not exactly a zip file because a zip file is lossless compression, What's happening here is a lossy compression. We're just kind of like getting a kind of a gestalt of the text that we trained on. We don't have an identical copy of it in these parameters. And so it's kind of like a lossy compression. You can think about it that way. The one more thing to point out here is these numbers here are actually, by today's standards, in terms of state-of-the-art, rookie numbers. So if you want to think about state-of-the-art neural networks, like say what you might use in ChatGPT or Claude or Bard or something like that, these numbers are off by a factor of 10 or more. So you would just go in and you would just like start multiplying by quite a bit more. And that's why these training runs today are many tens or even potentially hundreds of millions of dollars, very large clusters, very large data sets. And this process here is very involved to get those parameters. Once you have those parameters, running the neural network is fairly computationally cheap. Okay, so what is this neural network really doing, right? I mentioned that there are these parameters. This neural network basically is just trying to predict the next word in a sequence. You can think about it that way. So you can feed in a sequence of words, for example, cat sat on A. This feeds into a neural net, and these parameters are dispersed throughout this neural network. And there's neurons, and they're connected to each other, and they all fire in a certain way. You can think about it that way. And out comes a prediction for what word comes next. So for example, in this case, this neural network might predict that in this context of 4 words, the next word will probably be mat with, say, 97% probability. So this is fundamentally the problem that the neural network is performing. And this, you can show mathematically that there's a very close relationship between prediction and compression, which is why I sort of allude to this neural network as a kind of training it as kind of like a compression of the internet. Because if you can predict sort of the next word very accurately, you can use that to compress the data set. So it's just a next word prediction neural network. You give it some words, it gives you the next word. Now, the reason that what you get out of the training is actually quite a magical artifact is that basically the next word prediction task you might think is a very simple objective, but it's actually a pretty powerful objective because it forces you to learn a lot about the world inside the parameters of the neural network. So here I took a random web page at the time when I was making this talk. I just grabbed it from the main page of Wikipedia, and it was about Ruth Handler. And so think about being the neural network, and you're given some amount of words and trying to predict the next word in a sequence. Well, in this case, I'm highlighting here in red some of the words that would contain a lot of information. And so, for example, if your objective is to predict the next word, presumably your parameters have to learn a lot of this knowledge. You have to know about Ruth and Handler and when she was born and when she died, who she was, what she's done, and so on. And so in the task of next word prediction, you're learning a ton about the world, and all this knowledge is being compressed into the weights, the parameters. Now, how do we actually use these neural networks? Well, once we've trained them, I showed you that the model inference is a very simple process. We basically generate what comes next. We sample from the model, so we pick a word, and then we continue feeding it back in and get the next word and continue feeding that back in. So we can iterate this process, and this network then dreams internet documents. So for example, if we just run the neural network, or as we say, perform inference, we would get sort of like web page dreams. You can almost think about it that way, right? Because this network was trained on web pages, and then you can sort of like let it loose. So on the left, we have some kind of a Java code dream, it looks like. In the middle, we have some kind of a what looks like almost like an Amazon product dream. And on the right, we have something that almost looks like a Wikipedia article. Focusing for a bit on the middle one as an example. The title, the author, the ISBN number, everything else, this is all just totally made up by the network. The network is dreaming text from the distribution that it was trained on. It's just mimicking these documents. But this is all kind of like hallucinated. So for example, the ISBN number, this number probably, I would guess almost certainly does not exist. The model network just knows that what comes after ISBN colon is some kind of a number of roughly this length, and it's got all these digits. And it just like puts it in. It just kind of like puts in whatever looks reasonable. So it's parroting the training dataset distribution. On the right, the black-nosed dace, I looked it up, and it is actually a kind of fish. And what's happening here is this text verbatim is not found in a training set documents, but this information, if you actually look it up, is actually roughly correct with respect to this fish. And so the network has knowledge about this fish. It knows a lot about this fish. It's not going to exactly parrot the documents that it saw in the training set, But again, it's some kind of a lossy compression of the internet. It kind of remembers the gestalt, it kind of knows the knowledge, and it just kind of like goes and it creates the form. It creates kind of like the correct form and fills it with some of its knowledge. And you're never 100% sure if what it comes up with is, as we call, hallucination, or like an incorrect answer, or like a correct answer necessarily. So some of this stuff could be memorized, and some of it is not memorized, and you don't exactly know which is which. But for the most part, this is just kind of like hallucinating or like dreaming internet. Okay, let's now switch gears to how does hallucinating or like, and you don't exactly know which is which. But for the most part, this is just kind of like hallucinating or like dreaming internet text from its data distribution. Okay, let's now switch gears.
Okay, there was a lot of content over there, so let's break it down. Like first thing that he was talking was basically, uh, okay, how to create how those models are trained. Basically, creating those massive parameter files is like it is a very involved process, and as far as it is compared to just running the model, and training is a is very expensive or a costly process as well. For example, he gave an example of the llama 70b 70b model. So the training of that involved around feeding like 10 terabytes of text into the network and into the model, and also it was fed into like around I think I got the number around I don't know, to a cluster GPU cluster of 6,000 GPUs, and it was trained for run for around 12 days, and it costed $2 million to come up with those parameters. And and it is mentioned, and it is kind of a lossy compression of the entire internet, or the lossy compression of the 10 terabyte of data, or 10 terabyte of text is what is converted as 70 billion parameters. And after that, okay, once it is trained, and if we run that parameters with the run.c, we will get the inference, or we will get the value out of that model. So now the next thing, I think he mentions about the how it predicts and how it learns from the internet. Basically, spoke a lot about the lossy compression, and spoke a lot about the lossy compression, and also there is a concept like basically the dreaming effect. So whenever the network is learning about anything over the internet, basically in the screen that is currently shared, there are kind of three types of documents. One is a Java code, and the next one is a kind of Amazon product information, and the next one is the Wikipedia about something. So the network would know what is it like to be writing a Java code, and it knows how does a Amazon product description look, or the product details look, and what makes a wiki page or wiki format as well. And also it knows the knowledge about a particular product. Like if we ask like if it is if it was a part of the training document, but it does not it might or it may not produce the document as it was in the original document that was used for training. So it will hallucinate, and it will gather or remember from the training data, but it is a lossy compression. It is lossy compression means a lot of structure, or this could be lost in translation, but still it will make the best effort to convey the knowledge from gathered from multiple different sources. This process is called kind of a dreaming effect or the hallucination. So basically, like whatever the answer or the prediction provided is the best effort from the network or the model there. So let's get to the next section now. Before that, let's take a break, and I need to get to some work over there. Okay, welcome back. Sorry, today, as and when I come to sit here and study, like I'm pulled into some work related calls. I hope that doesn't happen again before we finish this. But yeah, but all, to summarize what we learned till now is basically we saw like what does a model or what does an LLM is consists of like basically two files or two different files. One is like the parameters, and the other one is the run.c. Run.c is a minimum 500 lines of code to execute the model, and then the parameters file is the like if a model is if an LLM model like Llama considered to be a 70 billion parameters, then each parameter might have 2 bytes, which make it 140 gigabyte sized file, and we can run it in our own MacBook to get the inference. So we ask a question on that model after running and get any answers that we need. And in the second section, the he was talking about like how that model is trained. Like for example, Llama was trained with 10 terabytes of text, and Meta has a paper written on it, and it was run on 6,000 GPUs, a cluster of 6,000 GPUs for 12 days, which costed them $2 million to train and generate those 70 billion parameters. So it kind of creates a kind of lossy compression of all the information or all the knowledge that it gets. And this is a kind of neural network. Basically, it is good at one thing, just predicting the next word or the next token. And as in when it predicts, like it feeds it back in, creating the long string of text basically. This is often described as kind of dreaming the internet documents. And then also, since this is a lossy compression, that the text that the model generates won't be always very accurate. It might provide the similar format, but it won't be the exact word. Like for example, he provided like, yeah, in the screen as we saw, if it is like a Amazon product description or a wiki page, it would be of the same format, but it would provide a ISBN number of that format, but the number could be from anywhere or whatever it is, like any random ones. So that is called hallucination. That is what they call refer to as hallucination. Let's keep moving forward and learn about it.
Here's to how does this network work? How does it actually perform this next word prediction task? What goes on inside it? Well, this is where things complicate a little bit. This is kind of like the schematic diagram of the neural network. If we kind of like zoom in into the toy diagram of this neural net, this is what we call the transformer neural network architecture, and this is kind of like a diagram of it. Now, what's remarkable about these neural nets is we actually understand in full detail the architecture. We know exactly what mathematical operations happen at all the different stages of it. The problem is that these 100 billion parameters are dispersed throughout the entire neural network. And so basically, these billions of parameters are throughout the neural net. And all we know is how to adjust these parameters iteratively to make the network as a whole better at the next word prediction task. So we know how to optimize these parameters. We know how to adjust them over time to get a better next word prediction. But we don't actually really know what these 100 billion parameters are doing. We can measure that it's getting better at the next word prediction, but we don't know how these parameters collaborate to actually perform that. We have some kind of models that you can try to think through on a high level for what the network might be doing. So we kind of understand that they build and maintain some kind of a knowledge database, but even this knowledge database is very strange and imperfect and weird. So a recent viral example is what we call the reversal curse. So as an example, if you go to ChatGPT and you talk to GPT-4, the best language model currently available, you say, who is Tom Cruise's mother? It will tell you it's Marilee Pfeiffer, which is correct. But if you say, who is Marilee Pfeiffer's son? It will tell you it doesn't know. So this knowledge is weird and it's kind of one-dimensional. And you have to sort of like, this knowledge isn't just like stored and can be accessed in all the different ways. You have to sort of like ask it from a certain direction almost. And so that's really weird and strange. And fundamentally, we don't really know because all you can kind of measure is whether it works or not and with what probability. So long story short, think of LLMs as kind of like mostly inscrutable artifacts. They're not similar to anything else you might build in an engineering discipline. Like they're not like a car where we sort of understand all the parts. They're these neural nets that come from a long process of optimization. And so we don't currently understand exactly how they work, although there's a field called interpretability or mechanistic interpretability, trying to kind of go in and try to figure out like what all the parts of this neural net are doing. And you can do that to some extent, but not fully right now. But right now we kind of treat them mostly as empirical artifacts. we can give them some inputs and we can measure the outputs. We can basically measure their behavior. We can look at the text that they generate and